Then so in the last class, we briefly talked about, so we basically, the rest of this chapter concerns different distributions, right? So we talk about uniform distribution, binomial, geometric, and so forth. The first distribution that we cover is discrete uniform distribution, because this is the easiest distribution. Basically, when we say uniform, we mean that basically all probabilities are the same, right? Constant probabilities. And we basically, I gave you the equation for the distribution. So so the equation was f of x for a uniform distribution between a and b is 1 divided by b minus a plus 1, right? But this is one of the easiest equations that you don't really need to memorize. The reason for that is the following. So imagine a case is usually more difficult when I have b and a, but it becomes super easy when I have numbers, right? So assume that my uniform distribution varies between 5 and 12, right? So since all of the distributions are the same, I can say that the number of these bars multiplied by f of x, because all of these guys are constant, all of them are f of x, same value, is equal to 1, right? That's one of the axioms of probability. The total probability is 1, right? So how many bars do I have here? The number of bars is actually b minus a plus 1, right? So since f of x times b minus a plus 1 is 1, therefore f of x is basically, that's the equation for the uniform distribution. And we also talked about the expected value, right? So we mentioned that the expected value is in the middle, a plus b divided by 2, right? So that means that if I have a uniform distribution that varies between 5 and 12, then 5 plus 12 is 17, divided by 2 is 8.5. So right here in the middle is my expected value, right? And the other thing I mentioned is that the expected value doesn't mean that this number is most likely to come, right? That's a very important mistake that many people make. The notion of expected value does not mean the highest probability outcome. Expected value means that in average, what value are we going to get, right? So I constructed this example intentionally so that the expected value, the probability of actually getting the expected value is 0, because there's no way that we get 8.5. All of these probabilities are 0, right? So for the uniform distribution, for example, all numbers are as likely, right? So 5 is as likely as 8, right? None of them has a higher chance, right? When we roll a die, 6 is as likely as 2, as 3, as 4.
Sir?
Okay, yeah, go ahead.
Would this formula for the mean be the same thing as the one we looked at previously, which was like x minus u squared times f of x?
Yeah, so that's an excellent question, right? Let me see. Yeah, so the question is, this formula, you know, is a specific formula for the, so there are more people in the waiting room. So this formula is specifically for the uniform distribution, right? And obviously it's different from the definition. The definition was mu is equal to sigma x f of x, right? So this equation is a definition of expected value, and as a definition, it always holds. This equation is specific for the uniform distribution, right? And it is a good idea to prove it. In fact, we are going to do this right now so that you see how we can start from the definition and get at the basically final answer. So we know that mu is sigma x f of x, right? And we know that f of x is a constant value, right? So for a uniform distribution, f of x is constant. So anything that's constant comes out of the sigma, right? So it basically becomes, maybe I can write it like this. So maybe x is equal to a to b, right? So I have a uniform distribution that varies from a to b. So I'm going to plug in. So it's going to be a f of a plus b, oops, sorry, plus a plus 1 f of a plus 1 plus dot 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 plus b f of b, right? So since I'm talking about the uniform distribution, f of a plus 1, all of them are constant, right? So they are the same value. So I can factor them out. And the value for that was 1 divided by b minus a plus 1, right? From the previous slide. That's the value of the uniform distribution times a plus 1 plus dot 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 plus b, right? All right. So now this is you had an equation for this. Let me try to remember. So the equation was 1 plus 2 plus dot 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 plus n is equal to, I think it was n times n plus 1 divided by 2, something like that. Let's check if this equation is correct. So let's check. Let's plug in n equal to 2. So 1 plus 2 is equal to 2 times 3 divided by 2, and that's 3. Yeah, so the equation checks. So this is the correct equation. So 1 plus 2 plus dot 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 plus n is n times n plus 1 divided by 2. So I'm actually going to use this this equation. So so basically what I'm going to do is I'm going to write down that is equal to 1 divided by b minus a plus 1 times. So this is from a to b. So what I'm going to do is that I'm going to write down it's from 1 plus 2 plus dot 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 plus b. So from 1 to b. And then I'm going to subtract 1 plus 2 plus dot 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 plus a, right? So that means that here I basically cancel out this additional term that I have added here, right? So these two terms in parentheses are the same. I just added here, this sum is from a to b. I just added 1 to a to it so that I can use this equation in green here, right? So these two are the same. And now I'm going to use the equation in green. So that is going to be 1 divided by b minus a plus 1 times, so 1 to b is going to be b times b plus 1 divided by 2. And 1 to a is going to be a times a plus 1 divided by 2, right? And now basically, I'm not going to do the rest because the rest is super trivial. You basically, you write out these, you expand these terms, and you basically get the same term here and here, they cancel out, and at the end you get a plus b divided by 2. Any questions?
I had a question about the slide, the previous slide. If that's
Sure.
okay.
Yeah, sure.
For f, the the fx equals 1 over b minus a plus 1. That's if all these like a equals 5, a equals 6, a equals 7, etc. If they all have a equal chance of occurring. That's correct, right?
Yes.
Okay. So it's not the case for I guess an experiment where not every outcome is, has a equal chance of occurring. That doesn't apply here.
Yes,
Okay.
absolutely. Yeah. Uniform means constant. So all basically, once we say uniform, we mean that all probabilities are equal.
Okay, thank you.
Sure. Any other questions? So the proof that I did here might seem, it does actually look, tedious, but the fact is that it looks tedious because I used numbers A to B, right? If I basically, instead of A and B, I used a uniform distribution that, for example, the example of rolling a die, right? So my A is 1, my B is 6, right? And f of x is 1 divided by 6, right? So in fact, we solved the expected value for this experiment before introducing this equation, right? Before I introduced the equation of the expected value, we calculated the expected value of the experiment of rolling a die using the definition, right? And our proof, if you look at the proof, it's in the video. It's exactly, I followed the same steps, right? The only reason that that was easy is that here, instead of A plus dot 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 plus B, all I had here was 1 plus 2 plus dot 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 plus 6, right? So we did this, manually, because this is an easy sum, just from 1 to 6. So the proof is for the uniform distribution is really easy. It just looks complex, but it's really easy. Any questions? Okay, so there are more people that have joined. Let me all right. Okay. So we just proved this equation, the previous slide. Of course, we can also prove the next one. It's a bit more difficult, of course, than the expected value. Basically, both of these equations are in the crib sheet. Of course, you don't need to memorize them, but the one at the top, is an intuitive one that you do need to know. It's important to know that when you have a uniform distribution, the average value is right in the middle. And I think you already knew that even before taking this course. Okay, so now the next distribution is binomial distribution. For the case of uniform, all outcomes were equally likely, right? It was a line. For the the remaining distributions that we cover, it's not a constant anymore, right? So these are, more interesting distributions. So to see why we cover binomial distribution, we have to look at basically the experiments that create binomial distribution. So instead of giving you the equation first I like to set up the problem for you. So assume that P is considered the probability of success in one trial, right? And I'm doing n trials, right? So whenever, if you want to visualize this, you can think about the following experiment. You roll a die 10 times, right? So if you roll the die 10 times, then P, and you have to define success as something, right? So let's say in this experiment of rolling the die, I define success as getting a 6. So in this case, P is equal to 1 divided. So in this experiment, P is equal to 1 divided by 6. And since I'm rolling the die 10 times, it means that I'm doing this experiment 10 times. So N is 10, right? And I define random variable X as the total number of successes, right? So in this experiment, X can be 0. I basically rolled 6 0 times, or X can be 1, or all the way to 10, right? So I can be very lucky, and all 10 times, you know, I get a 6. And a very important keyword here is that the trials are independent, right? So if the trials are not independent, then your distribution is not binomial, right? So when I'm rolling a die multiple times, the second roll, the first roll does not affect the second roll, and the second roll does not affect the third roll, and so forth, right? So every roll is an independent experiment, right? And the goal is to find f of x, right? So the goal is to find out what's the probability of getting, you know, 2 6s, or what's the probability of getting 3 6s, what's the probability of getting 10 6s, right? So we can clearly see that these probabilities are not equal, because just from intuition, we know that f of 10 is very small, right? That means that getting 10 6s in this experiment is an unlikely outcome. Okay, so the equation to find f of x is the following. So it's basically, it's n choose x times p, probability of success, to the power x, times 1 minus p to the power n minus x, right? For x equal to 0, so we don't have any success, 1 success, or all of the experiments are success, n successes, right? So let's look at this example. Let's try to solve this using the equation. We roll a die 10 times. So we say that, okay, we are rolling 10 times. So this is our n. N is the number of experiments. What's the probability of getting 6 three times? So the success is defined as getting a 6. So p is 1/6, right? Because all numbers on the die are equally likely, the chance of getting, you know, any particular number is 1 divided by 6. And we want to succeed 3 times. So that means that our x is 3, right? So, you know, when we identify n, p, and x, we are done. So we simply say that f of x is n choose x times p to the power x times 1 minus p to the power n minus x, and that is equal to 10 choose 3 times 1/6 to the power x, which is 3, times 1 minus p, which is 5 divided by 6 to the power n minus x, which is 7. So that's it. That's our answer. Any questions?
Yeah, what's the first product? Like, what's the first factor in the product?
Yeah, so this is combination, right? So this basically means that, so perhaps we should continue. So maybe I can write here. So n choose x is equal to n factorial divided by x factorial times n minus x factorial, right? So in this case, that is going to be 10 factorial divided by 7 factorial times 3 factorial times 1/6 to the power 3 times 5/6 to the power 7. So that's the final answer. Did I answer the question?
Yes.
Okay. Any other questions? Okay. So In my opinion, it's important to know why this equation is correct, right? It's not a good idea to, just use equations without knowing where they came from. And knowing actually where they come from, even for this course, it will help you to use the right question, right? The right equation, because we will introduce many equations later on. And if you don't know, if you have no idea where the equations came from, it will be hard to know which one to use, right? So basically, to find out where this equation came from, let's solve this other question, right? So we roll a die 10 times. What is the chance of the following outcome? Right. So the outcome is the following. I have, for example, S indicates success. So S, success, failure S, failure S, and then the rest are all failures. F, 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 F. So let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9. I need one more F. 10, right? So I'm rolling the die 10 times. In the first trial, I get a 6. Second trial, I don't get a 6. Third trial, I get a 6. Fourth trial, I don't get a 6. Fifth trial, I get a 6. And then all of the remaining ones, I don't get a 6, right? So basically, this is an easy question that you should be able to solve very quickly. The chance of this happening is basically P of this outcome is equal to, so I want the first outcome to be S, right? So this is equal to P of, so basically, let me try to be concise. So this means intersection, right? I want the first to be success, the second to be failure, and so forth, right? So there is an intersection in between these guys, right? And between all of them, right? And since I say, since I know that when I roll a die 10 times, these like second roll is independent from the first roll, right? So I'm going to use that easy equation that we had, that if A and B independent, then I can say P of A intersection B is simply P of A, P of B, right? So since I know all of these experiments, the first roll, second roll, all of these are independent, I'm simply going to write down the product. So S P of F, sorry, right? All of them. So what's the chance of success in the first trial? That's going to be 1 divided by 6, right? Because in the first trial, I have 6 possible outcomes. Only one of them is defined as success. So the chance of success is 1 divided by 6. The chance of failure is 5 divided by 6, because any other number that comes out except of 6, I have basically failed, and so forth, right? Right. So when I write that, that's going to be, how many successes do I have here? I have 3 successes. So that's 1 divided by 6 to the power 3 times, how many failures do I have? 5 divided by 6 to the power 7. I have 7 failures, right? So you can immediately see that this term in our previous answer came from here, right? So a certain outcome, the chance of getting that certain outcome is basically this quantity, right? But if you look at the previous answer, we are multiplying that by a relatively large number, right? So this number, I think this is around like So I'm trying to figure out what this number is around. So this is 10 times 9 times 8 divided by 6. So this number is around 100, right? So we are multiplying whatever this number is by something around 100. Can somebody please calculate it? I want to make sure what the exact number is.
It's 120.
120, thank you. So this number is 120. So we are multiplying this small number by 120, right? Why are we doing that? Any ideas?
I have an idea.
Yeah.
It's because the outcome where the success is 3 times can be not exactly this order. It can be like different orders. So that's why we take different combinations.
Exactly. Yeah. So that's exact. That's even better than what I wanted to say. So so basically here in the original question, we wanted getting 6 3 times. We didn't care about the order, right? All we wanted was getting 3 6s, right? In the follow-up question that I gave, I wanted the successes to happen in a particular order, right? So the first success, the third success, and the fifth success, right? But remember, this is not the only outcome that satisfies this question, right? As your colleague said, there are many of these, right? For example, I can have S, 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 and then all of the rest failures, right? Or I can have, you know, so many of these, right? So the question is, how many of these do I have, right? And here is where you have to use the counting technique that we talked about, combination. So the question is, I have 10 trials, right? Trial 1, trial 2, trial 3, trial 10, right? I have 10 total trials, and I want 3 of these to be success, right? So all I want is I want 3 out of these to be success, success, and success, right? What's the chance of that? It's the combinations of 3 out of 10. So that's what this number is. That's where this number is coming from, right? So now you know the proof of binomial distribution, and I think it's very important, not just for this course. I think in your life, it's important to know, you know, how to manipulate, you know, individual probabilities and then add them up. Basically, all we did here is that we calculated one probability and then multiplied by the total number of outcomes that we had, which is this number here. Any questions?
Can you explain the factor on the left again? I'm not sure I got it.
Yeah, yeah, sure. So this number, right? The factorial guy?
Yeah. The 10 factorial divided by 7.
Yeah, sure. So basically, in the original question, we want to have 3 successes, right? So we have a total of 10 trials. We want to have 3 successes. We want to find out the probability of that. So basically what we are doing, I'm saying that, okay, I have, like, we can think of this as like 10 different.
Yeah, it's like 10 different permutations, or like you can have 10 different sequences. Yeah, I understand that.
I wouldn't say permutations. I would say combinations, because permutation was a different thing. Yeah, so basically, I think a good way to think of it is the following. So how many ways can I have, you know, 3 successes out of 10 trials, right? So you can think of, you know, the 10 trials as 10 balls, right? And then I want to basically select 10 balls to put, for example, success inside them. Right?
Okay.
So I have 10 balls. I want to select 3 of them to basically be success, right? So how many ways can I do that? I have 10 balls. I want to select 3 of them. It's combinations of 3 out of 10. And if I select these 3, it's going to be this, this, and this. And all of the rest are failure, right?
Yeah. So it's essentially like the positions of all the successes, like in the balls. Yeah.
It's the position of all the successes. Yeah.
Okay.
And that is
so
combinations of basically 10 out of 3.
Oh, okay, so that's literally that factor on the left is exactly that. Okay, I get it now.
Yeah. So this
Yeah,
is so the proof for this is also very interesting. I proved this, why this is the case. This was one of the counting techniques, right? So the first counting
okay.
technique was permutation. The second counting technique was combination. So this is combination.
Yeah, okay. That makes sense. Thank you, sir.
Yeah. Other questions?
Yeah.
Yeah.
I have a question about the follow-up question that you wrote.
Mhm.
So like for any sequence that we want, the probability will be same.
Yeah, okay, that's a good question. So basically the question is the following. So the follow-up question that we wrote, so the question is, we roll a die 10 times and success is defined. So let's write it. We roll 10 times. Success is defined as getting a 6, right? It doesn't matter what number I write here, right? Getting a 6, getting a 1, basically all we care about is the chance of success, right? So that means that P of success is 1 divided by 6. Now the question is, what is probability of, for example, S, and then F, F, right? So, so this probability, since they are independent, is going to be the multiplication. And when I multiply, basically it's going to be 1 divided by 6 times 1 divided by 6 times 1 divided by 6 because of the 3 successes, right? And then times 5 divided by 6 to the power 7, because here I have 7 failures, right? The order doesn't matter. So no matter what the order is, I'm always going to arrive at the exact same thing. So for example, P of S, F, S, F, dot, is equal to the exactly same thing. So these two are equal. Right? Because the reason for that is that the following one is going to be 1 divided by 6 times 5 divided by 6 times 1 divided by 6 times 1 divided by 6 times. So how many failures do I have here? 6, right? 5 divided by 6 to the power 6. And I have 5 divided by 6 here, another 5 divided by 6 here. So it becomes to the power 7, which is the same as what we had before. So the order doesn't matter. All of them are equally likely. That's actually a good question. So this is a uniform distribution, right? All of these are equally likely. So that means that this is a uniform distribution.
But if the probability remains the same for every case, then how come the answer is different from the original question?
Oh yeah, so because probability is the same for each one of these guys, right? But all of those satisfy the original question. The original question said we want to get a 6 3 times. If you look at these, in all of these, I'm getting a 6 3 times, right? Here I'm getting a 6 3 times, right? So to find the final answer, what I have to do is I have to add up these numbers, right? So my final answer is going to be this number plus this number plus the next one plus dot plus all of these, right? And I basically have to add all of these up. How many of these do I have? The number of these that I have is 10 choose 7. So the answer becomes 10 choose 7, or combinations of 7 out of, I should have written 3 choose 10, but these are equal, right?
Yeah.
I think I talked about it before. So 3 choose 10 and 7 choose 10 are the same number. So it's 10 choose 3 times the previous answer, 1 divided by 6 to the power 3 times 5 divided by 6 to the power 7. Was that the question?
Yeah. Thank you.
Yeah. Other questions?
Yeah, so I just wanted to ask, when would we use like this method compared to what you showed before? Like why can't I just always do this? It seems much simpler. There's like less work involved. You just multiply the amount of successes by failures, and then it'll give you the probability, right?
Yeah.
So why would we
Versus,
do another method?
so, I mean, in this case, we could, in this case that I wrote here, I'm not sure if I understood the question. So in this case, I can basically write down the probability. In this case, I can't, because there are many ways I can get 3 successes out of 10 trials, right? Because I don't know the first 3 are going to be the success or the last 3 are going to be the success, right? So basically what I did is I broke down this original problem into many smaller problems that are manageable. Was that your question?
Okay. Yes, yes. Okay, I see. Thank you.
Yeah. Any other questions? Okay. So yeah. So basically, the final answer is we simply use the equation, right? Oops, I don't know why this sometimes. So the final answer was 10 combinations of 3 out of 10. So sometimes I call this as, I refer to these combinations of 3 out of 10 as 10 choose 3, which is the same thing, right? We have 10, we want to choose 3. It's the same thing as combinations of 3 out of 10 times 1 divided by 6 to the power 3 times 5 divided by 6 to the power 7. Okay. All right. So the next question, we flip a coin 20 times. What's the probability of getting 10 heads and 10 tails, right? So again, I'm not going to prove this one again because you only prove the equation once, right? So in this case, I'm simply going to use the binomial equation. But I think for your own practice, I mean, I don't think for your own practice, do solve this equation without the equation do solve this question without the binomial equation. Let's see if you can arrive at the same answer. So we flip a coin 20 times. What's the probability of 10 heads and 10 tails? So that means that n is 20. X is 10. I want, basically, in this case, it doesn't matter what we define as success because head and tail are equally likely. So X is 10 and P, the chance of success is 1 divided by 2, right? So that's it. The answer is going to be 20 choose 10 times 1 to the power 2 to the power 10 times again 1 divided by 2 to the power 20 minus 10, which is again 10, right? Or can simplify that as 20 choose 10 divided by 2 to the power of 20. Any questions? Okay. Let's continue. So this is a question from the midterm exam last year, actually in the fall. So if last month, actually in December. So the question had, I think, 3 parts. We only solved the first part because the other parts have not been covered yet. So a new space exploration company expects to receive orders to manufacture 200 space rockets in the next year, a 20% increase from its current year's orders. Manufacturing a space rocket requires carefully assembling more than 300 parts. 70% of rockets manufactured by the company passed the quality test, QC. Okay. If a rocket passes QC, so when I read the question, so the questions, for this course, and in my opinion, questions that are worthy of your time are usually long questions, right? So you have to be able to summarize the information. I always like to highlight the numbers because usually numbers are important. So 200, 20% increase, 300 parts, 70% pass QC. If a rocket passes QC, there is a small chance of an accident. So 0.1% chance of an accident. Rockets are safe. Okay. So find the probability of 2 rockets failing QC if 10 rockets are tested, right? So yeah, so we immediately see this is binomial because I'm testing 10 rockets, right? So basically means that I'm repeating the experiment 10 times. So I immediately see that this is binomial. This is my n, right? The total number of my experiments is n. I want 2 rockets to fail. So this is my n. So in this experiment, failing is defined as success, right? So for the case of the binomial distribution, success basically here is defined as having a rocket that actually, finding a rocket that actually fails, right? So n is 2, sorry, x is 2, x is 2. And I have n and x. All I need to do is to find the chance of failing, right? Probability of success. So probability of failing is equal to this guy here. There's this guy, right? So that is 0.01%. So that is 10 to the power minus 4, right? So that's it. All I need to do is to plug in the numbers. So my answer is going to be P is going to be equal to 10, choose 2, times 10 to the power minus 4 to the power 2. Just one second. Just one second. 1 minus 10 to the minus 4 to the power 8, right? Yeah, go ahead.
Isn't it the probability to pass the QC test 30%? Because in the problem it says 70% will pass the quality test.
Oh, yeah, thank you.
Yeah. And 0.01% is just.
Thank you very much. Yes, that is correct. You are. Yeah, I did make a mistake. Yeah,
No,
I didn't read the question properly. Thank you. Yeah, I used to give chocolates before when somebody found my mistakes. So you are right. I did make a mistake. So the question is explicitly asking for failing QC, and the question says the probability of failing QC is 70%, right? So what I wrote here is incorrect because I wrote the probability of the rocket failing, right? I didn't read the QC part. So the final answer is going to be, so this is wrong. The answer is going to be P is going to be 2 out of 10 times 0.7 to the power 2 times 1 minus 0.7, which is 0.3 to the power 8. So that's it. So basically my mistake was P of F is
Excuse me, sir.
Oh, actually, I think I made another mistake. Just one second. I think I'm being I'm rushing through. So 70%. So the question says 70% pass QC, right? And the problem was failing QC, right? So probability of failing QC is going to be, so this is 0.3. So I made another mistake. So this is times 0.3, because here this is probability of passing QC. 70% passes QC. So probability of failing QC is 0.3 to the power 2 times 1 minus that, which is 0.7 to the power 8. Was that your question that I made a mistake? Yeah, so don't, I see somebody raise the hand. So you can unmute yourself and ask the question.
Yes, so would you just be able to just quickly re-explain the formula you wrote? I got a little confused there.
Yeah, sure. Yeah, I was going to do that. So let me add a slide here. So probability of failing QC. So the question tells me that if I pick one rocket, the probability of that rocket failing the QC is 30%, 0.3, right? And I'm picking 10 rockets, right? So that means that my N is 10, right? So I'm picking 10 rockets. Each of these rockets has a 30% chance of failing QC. The question asks, what is the probability of finding 2 rockets that fail QC, right? So that's the question. What's the probability of finding 2 rockets that fail QC, right? So basically I say that, okay, that means that out of n trials, I want my X to be basically 2, right? And you know, so in this experiment, you know, every rocket has a 30% chance of failing, right? So basically, these are, I mean, the question didn't really tell us, but we can, you know, like induce from, you know, our own knowledge that rockets are independent from each other, right? So if one rocket fails the test, it doesn't mean the next one, you know, is not going to fail the test. So since these are independent events, we are going to use the binomial distribution. So the answer to P is going to be N choose X times P to the power X times 1 minus P to the power N minus X, right? So all I have to do now is to plug in numbers. N was 10, X was 3, P was 0.3 to the power 3, and then 1 minus P is 0.7 to the power N minus X, which is, oh,
Isn't it, yeah, 10 choose
Yeah, isn't
2?
it 10 too?
Yeah, sorry.
Yeah,
Yeah, that's
yeah.
yeah, making too many mistakes. Thank you. 10 choose 2, and then 0.3 to the power 2, and then 0.7 to the power 8. Any questions? So before I answer questions, let me solve the exact same question using another approach. So probability of failing QC is 0.3. I could write it as following: probability of passing QC is 0.7, right? So here I take this as my success. So here I define success as, you know, passing actually QC. So again, I pick 10 rockets, so my N is still 10. And instead of finding 2 rockets that fail QC, so in the previous question, I wanted 2 rockets that fail, and I had the probability of failing. In the new question, I'm going to write down probability of finding 2 that fail is equal to probability of finding 8 that pass, right? Because finding 2 rockets that fail, it means that the eight remaining ones must pass, right? So now I'm going to use, this is equal to P of X equal to 8, right? And then that's going to be exact same equation. I'm not going to repeat it. That's the equation of the binomial. I'm just going to plug in the numbers. So that's going to be 10 choose 8 times probability of success, which is 0.7 to the power 8, times probability of 1 minus success, which is 0.3 to the power 2, right? And I leave these to sort of like an exercise at home. These 2 numbers are exactly equal. These are the same numbers, right? And the reason for that is that 10 choose 2 is equal to 10 choose 8. These 2 are equal. Both of them are 10 factorial divided by 8 factorial times 2 factorial, right? So it doesn't matter if you have 10 objects, the number of times you can select 2 objects is equal to number of times you can select 8 objects.
I have a question, sir. So we don't use the 0.01% anymore?
No. So this question had multiple parts, right? So some of the other, numbers are used in the following parts. But that was my mistake, right? So the question says this is the probability of a rocket, failing during an actual flight. The question wants the probability of failing QC, right? So this number is completely irrelevant.
Okay, I see.
Yeah, many numbers are irrelevant. This is irrelevant. This is irrelevant. Yeah, so I see if you have any questions, you can go ahead and ask. I see some people have raised your hands. I don't actually see who it is.
Yes, sir.
Yeah.
For binomial distributions, are the events always going to be independent?
Yes, very important. Yeah, they have to be independent.
Okay.
Other questions? Okay, so let's move on. So I have an urn. So this is the next question that we want to solve. We have an urn that contains 10 green and 20 red marbles, right? So 10 green and 20 red, right? 6 marbles are removed one by one with replacement, right? So that means that when I remove one marble, I look at the color, I put it back, I remove another one. What's the probability that all marbles are red, right? So in this experiment, since after looking at the marble, I put it back, the probabilities are independent from each other, right? So that means that if the first one is red, it doesn't affect the chance of second one being red, So since these are independent, I can use the equation for binomial distribution. So I'm going to say, I'm removing 6 marbles. So n is 6. The number of trials is 6. I want all marbles to be red. So that means that my x is also 6, right? And what's the chance of success? So I have 20 red and 10 green. So P is 20 divided by 30, right? So now all I have to do is to plug into this equation. N choose x times p to the power x times 1 minus p to the power n minus x, right? Which is going to be 30, choose x, which is 6. Or just 1 second, I think I'm making a mistake. So n is again 6, x is also 6 times p, p is 2/3 to the power x, which is 6 times 1 minus p to the power n minus x. So n minus x becomes 0. So this becomes anything to the power 0 is 1. So times 1. So that's the answer. So the answer is 2 divided by 6 divided by, 2 to the power 6 divided by 3 to the power 6. That's the final answer.
So why is it 6 choose 6?
Because I want all marbles to be red, right? So when I say all marbles to be 6, that means that the number of success is actually 6.
Okay.
Sir?
Yeah.
Couldn't we do 20 over 30 multiplied by 20 over 30 6 times?
Exactly. Yeah.
Yeah.
Yeah, that's an excellent question. Yes, that is correct. So basically for this question, I didn't actually need to use the binomial equation. All I could do was to say, I'm doing 6 independent experiments. I'm going to multiply the probability of each experiment by each other because these are independent. So I'm going to say the probability of success in the first trial is 2/3, right? the first marble to be red, the chance of that is 2/3. The chance of the second marble to be red, that's the same, 2/3, times 2/3. And that's the same answer. It's going to be 2/3 to the power 6. So for this example, we didn't need to use binomial, but for the next part, it becomes difficult if we don't use binomial, right? What is the probability that 4 marbles are red, right? Because now I can't really solve it using this equation because I don't know which 4 marbles are red, the first 4 marbles or the last 4 marbles, or, you know, they are staggered. Did I answer the question?
Oh, yes, thank you.
Okay, so let's do the next one. So in the next one, you know, n doesn't change, of course, n is still 6, but here I want 4 successes, right? So I want 4 marbles to be red, and P of success is still 2/3, right? So I'm not going to repeat the equation. I'm going to use the same equation. So the answer is going to be 6, choose 4, times 2/3 to the power x, which is 4, times 1/3 to the power 6 minus 4, which is 2.
I have a question about the first part. So, I don't know how it's called, like the number of combinations. Since you have n and x being 6, wouldn't your like subtraction, because it's n divided by like n factorial divided by x factorial times n minus x factorial, right? So you would have 6 minus 6.
Yeah. So this is something that it's important to remember. N choose n is going to be n factorial divided by n minus n factorial times n factorial, right? And that is going to be equal to, so these two cancel out, right? So that's going to be equal to 1 divided by 0 factorial.
Over 0, which is good. Okay. Yeah. Okay.
And 0 factorial is 1.
Oh, okay. So that's the thing I'm missing. Okay.
Yeah.
I didn't know that. Thank you.
Yeah, sure. So remember, n choose n is 1, and n choose 0 is also 1, right? So how many ways can you have 0 successes, right? There's only one way, because all of them have to be, you know, failure if you want 0 successes, right? So n choose n and n choose 0, both of them are 1, no matter what n is.
Yeah. Okay, I see. Thank you.
Yeah. Any other questions? I think that's the last slide that I wanted to cover. So now I'm going to first stop recording, and then I'm going to look at the chat box. And then if you have any remaining questions that you didn't want to ask during the recorded session, you can ask now. So let me.
Is the lecture over?
No, the part that I record is over, but the lecture continues. So let me.